Welcome everyone. Thank you for joining this session. It's gonna be the first week of the lab three. On the lab three, we're gonna focus on the orbits and the mechanics of the celestial object that is running around the big objects like a gas giant in the solar system. And I believe that's gonna be a very fantastic opportunity for all of us to learn more on the discoveries that Galileo made about more than 400 years ago. And we get just go over some geocentric and uh, uh, heliocentric visions of the sky around us. Before going through that, if anybody had anything to add before starting to the objects, the background and information. Any question from the previous labs and one and two? Ray or John?
One thing I'm going to push out too is we are coming up on March 14th. So there is a lunar eclipse coming up, something worth watching, especially in lieu of this lesson and talking about Galileo and his research discoveries on the moon and the sun. Um, that it also is getting close to the longest, I mean, not the longest day, the spring equinox is coming up, but also Mercury is finally kicking out, and it'll be as far out as it's going to be, I believe, on March 14th. And then it'll start coming back in. And so if anybody wants to make any images, I know I'm going to try to bank some images of Mercury if I can to see what telescopes actually are situated to pick it up. While we have an opportunity, because it won't last long. And it's also a neat object to actually see in the evening. I know we have a star party coming up, and hopefully we have a nice clear sky. We can see it because it'll be up, and then about a week or it'll be gone again. It just doesn't stay up very long for an object to see in the sky.
And also another opportunity is that because lunar eclipse is a longer duration than the solar one, that is few minutes, that's gonna be few hours. Therefore, hopefully sometime, although based on the weather condition that I see it is kind of fair on that region that we are here on the North Carolina, South Carolina, but hopefully by that time, because gonna change and hopefully have a clear sky, we can have some view or take a photo, whatever we can to engage this beautiful eclipse. Okay, let me share the material, start the uh, subject in here. Mm.
Yeah, we had a few things that did come up last session that I had that may not have come up last week. We talked a little bit about just red night vision, the idea of using, if you do observations, stellarium quite often has an option to go to a red mode, and that's really for people to observe in the evening. Let's recapping on that. And we talked about noon and the idea that different train stations back in the day used to designate, somebody would actually designate where noon was, depending where you're at. But we're moving past that today into Keplerian motion. And there's a lot of fun history with Kepler also. You know, you've heard me talk about Brahe, and actually had a chance to go to Copenhagen and try to look for Brahe. And I thought it'd be worth taking a trip out to his island to see his observatory. And then I found that basically it's all gone. He was a very unpopular fellow. He even did not get along with his parents or anybody, but he was instrumental. His data was instrumental for many people, like Kepler, who would be after, I believe, Galileo in time.
We're able to see it or no, not?
Oh, they scrubbed it out. In fact,
Really?
what I always heard was he was so unpopular that his folks were so wealthy that they bought this property so they didn't have to see him anymore. That he'd be at a distance from them, they wouldn't run into each other very often.
Oh, really?
He had a hard time getting along with people. And the story I've always heard was, Brahe died at a party from what was said to be an exploded bladder from not relieving himself. And the doctor who did the autopsy was actually Kepler, because he was a resident, the person with the degree who could do that, who pronounced that. But they exhumed his body 100 years later and found that that was not true. So the rumors have always been that Kepler had a dark side to him, And he did not get along with Brahe either. But he once they had the data he needed, he basically instead of leaving the island, he actually stuck around, and Brahe was no more.
Good. Thank you for that historical note. Very great. I mean, that's the kind of one of the key features that make it modern astronomy alive today. We have okay. We go on the lab tree. We have four objectives. We have measure the moon's orbit around the planet. Mostly, we're gonna focus on the gas giant like Jupiter, Saturn, Uranus, and Neptune, and use this information to measure the mass of the planet, either of the gas giants. And then based on that, we measure the also angular size and phase of the Venus and compare it on the geocentric and heliocentric uh, theories of the consideration on the sky movement, and also use this information to distinguish, as I mentioned, between these two items. That's actually observing the angular diameter and phase of the Venus is one of the key features that made it Galileo help to prove the heliocentric models on the sky. Basically, the Galileo in 1609, they made a four revolutionary discoveries that made it uh, existing theories or models of the sky at that time in the question. And one of them was about the majority of the items that they see it like a sun and moon. They thought the people is very smooth and kind of very uniform circles and or disks, and they don't see it kind of they may have uneven or blemished surface, dark and white, and different features. As you see it with the simple bino, you can easily binoculars. You can see it also by your eyes. Also, you can distinguish the dark side and uh, white surface on the moon, and also same thing on the sun by the solar telescope. You can see it the sunspots and other features like flares or prominences on the around the circle. If you have a proper safe telescope to look through it. On the other hand, this historical picture, that handwriting of the Galileo about the uh, different orientation of the Galilean moons, four moons of the Jupiter on different days and times that he observed, it shows exactly not everything is kind of moving around the Earth. We don't have geocentric. This is the one simple contradiction of the that conceptual model that they have as a geocentric, that there is some celestial object exist like Jupiter. There is another object like a moons of the Jupiter moving around it. And that's one of the key features that he discovered. And on the other hand, also he observed the uh, uh, crescent and the different phase of the moon, Venus as well. As you see it, Venus comes with a small, when it is far away from us on the other side of the sun, it goes to the closer to us when it gets the new phase of the Venus in here. It's actually based on the geocentric model. The model was consist of the epicycle running around the Earth on the center, and we call it that the different the orbit of the object around it. That is based on the Aristotle and Ptolemy model they created like that. If we see it, the um, Venus phases like that. If we start from here, that is new phase, we see it, uh, we don't see it anything from the Venus because actually between us and the sun. This is based on the geocentric model. If we move it this way on the right side on the cycle, it goes like a crescent, make it bigger and bigger, but we don't see any quarter cycle. It doesn't mean that 50% of the Venus become full by this time. And then again, we're gonna reach to the new phase waning and waxing moon on here, and then cycle back with a larger crescent on this Venus and go back to the new. If we graph the kind of this condition, it's going to show us like this. On the first, we have a new moon, where this is closer to us, angular diameter is larger on here. And then it goes to number two, it is a kind of crescent, but it is a little bit farther down. At the end, when we reach to the farther side, closer to the sun and farther away from Earth, we're going to back to the new phase again, number three, and go back four and come back one. It's going to show us some this kind of area of the uh, kind of curve that's showing the crescent phase versus the angular diameter. This is based on the geocentric model. If we assume everything is moving around the Earth, but if we go with a more systematic uh, heliocentric center model that the sun is on the middle, we have different idea. On the new moon, we have similar way. We don't see it. The Saturn gradually crescent become larger and larger. Then we have waxing uh, uh, phase, and then we get the full. And then after the full, it comes back to the waning and again smaller crescent and back to the first place. If we graph this model, gonna be something on the red curve that we showed here, and it is completely different. If we just observe the Venus, it's gonna provide for us very good kind of not actual proof of the heliocentric, but it is a kind of very close idea that by observation we can identify this. Whatever we know about the geocentric model, something is wrong, and we have to differ to the more reliable and the heliocentric one. And you can do it on the home by a very simple example. You have a sheet and you have some pinpoint here. You just stretch it the uh, pen by a um, kind of a simple device and try to stretch it as much as you can and just draw it on the piece of the paper. Whatever orbit you get it, it's going to be ellipsoid. It's not a circular because we have 2 points, two focus point that we have here, just center of the ellipse. And this movement is totally different than the circle. And this shows that Kepler basic law, three laws that he invented and created on the early 1600, that shows the planets orbiting the sun is not and the moons are orbiting the planets, not based on the circle but ellipses. And this one is a basic kind of modern technology of the astronomy comes to the science. Therefore, but based on this, one of the major parameters that we have to remember. We have a longer axis, we call it major axis. We have another one across this direction perpendicular to the major axis, we call it minor axis. And one of the important factors that we're going to look through on this lab is semi-major axis. I mean, we call it by denoted A. It means that whatever dimension we're going to get here, half of that going to be from this point to the age of the orbit. And this was shows in A here, and this is a kind of very sample presentation of the Kepler's third law. It says that if we cube this semi-axis measure for any planet around the sun, if we cube it, it's going to be proportional with the uh, orbital period that we showed with P here square. Therefore, this is very closely applicable for majority of the planet except Mercury that has some deviation because of the very close to the sun. But on this Venus, Earth, Saturn, uh, Mars, Jupiter, and all the planets are very closely this valid. At that time, Kepler doesn't know that what the constant means. But later on, Newton discovered the kind of formula for the gravity, and it found out that constant is comes 4 times pi square divided by gm. G is the constant gravitational constant for the solar system that we have, and m is the uh, solar mass. The solar mass is actually main body of the orbit. If we are looking for the planet orbiting the sun, m gonna be what to call it, mass of the solar. And if we are looking to orbit of the moons of the gas giant, for example, Jupiter, m gonna be mass of the Jupiter. To calculate this one a little bit very difficult to equation. You have to do kind of substitution between the parameters that you have on this formula, but we consider very simple way. This is the way that we gonna use. We don't want to go calculate whole detail of this g value and m value, a and p. We're gonna do based on the ratio and proportionality. We assume one of the equation, this equation for Earth. This is for the Earth. Uh, what the solar the period that we have for the Earth, p, orbital period for the Earth, gonna be 1 year, and a semi-major axis for the Earth gonna be 1 AU, that is distance between Earth and Sun, and then m gonna be solar mass of the Sun, and g is a constant. And the next one, we're gonna look through one of the planets. For example, we call it P, uh, for example, for the planet, and m gonna be here as showing the mass mass of the Jupiter. If we assume Jupiter, if it is Saturn, that's gonna be mass of the Saturn. If divided these two equations together with a proportionality, we get this equation. Then g is cancelled out because they had in both of them. And if we just substitute and calculate the m, it's going to be easily calculated by this way. You calculate the A and you calculate the B versus the Earth parameters based on the AU and 1 year, and times the mass of the sun. We're going to get the mass of the planet. Therefore, for this activity, that's going to be a simple way that we're going to do. On the observation that we have on the Skynet, we're going to provide these parameters. I told you this on the previous, we told you that on the previous session, when you want to take a picture of the planet, you have different values. But when you want to get the picture of the planet and the moons, you're going to use different exposure value and filters. Here for the Jupiter, we recommended to use V 0.03 second. And for the Saturn, Uranus, and Neptune, all of them, we're going to use high Q. High true is the kind of filter that is using for the faint object. And the faint object is not the Saturn or Uranus and Neptune, probably. It's more related to the moons around those gas giants. Therefore, we're using these values, and for the Uranus, we're using 1 second and 1 second. And this one values that we have here is only for observing the um, uh, planet plus the moons. And here another change we're going to have on the Skynet. And on the previous times that we have on the Skynet, we didn't have this one. But in here, we're going to have continuous pictures on several times. We're going to say sequential filter. We're going to use here continue the next available telescope. We highlighted this one. And we say repeat this observation for 14 times with at least 1 days apart when they apart each other. And then based on this configuration, I'm going to show you on the Skynet as well. Then we're going to get about 14 pictures for each giant and the moons. And for example, if we want to use the uh, for the Jupiter, we're going to focus on the Ganymede. All of them is the brightest and the largest moons. We're using this largest moons because it's more easier to observe and more weight and effective on the orbit to consider. We don't want to go very smaller moons of the gas giant here. For the Jupiter Ganymede, for the Saturn Titan, Oberon for the Uranus, and the Triton for the Neptune. And after we did this, therefore, we're going to come here and provide what they call it, Julian Day. Julian Day, probably, if you know, or I can bring it here as well. Let me see. I have recorded somewhere. It is a kind of a specific target number of the days. The reason we're using Julian days here, normally in most of the astronomical observation, we're using this Julian day for the uh, kind of approach and kind of origin for the calculation of the number of the days. Because if we're going to go based on the different calendar system that we have, that's going to be very difficult to calculate the exact number based on the different references. This reference is based on the year 4713 before Christ, BC. It is actually invented and adopted by one of the astronomer in 16th century, 1583. Uh, uh, that based on that, we just calculate that one. One of the item that you can calculate is here astronomical application department of the U.S. Navy that you can easily go every day that date you have here, easily calculate the Julian day as needed here. And or if you have a Julian day converted to the regular calendar day based on the UTC or uniform Greenwich time zone. And if we go back to here for the observation, uh, in this session, we're gonna look through again one of the planets, Jupiter. As we see it, Jupiter is here. Then we go uh, nighttime to see. Hopefully, we can see it. Let me show it the different. The sunset. Okay, and we can enlarge it here to see it more closely if we need it. Okay, then and here everything is given here. We put different name. For example, Jupiter moons. I put my name, initial March 2000 or 25, something like that. To be later on, you can distinguish it. Then here we're gonna go to the advanced item that I identified before. As you see it here, Jupiter is very easily observable on majority of the telescope that we had on the uh, Skynet. And things that we're gonna do here, that's kind of advanced setting that we're gonna do to repeat the observation. Let me see, where is the repeated observation? Might be, we have to specify somewhere else. I don't see it here. Let me go back to the target to see where it is identified. Okay, advanced option. And in here, we have to use the advanced option tab and select repeat the observation. Then here, advanced, let me see, repeat observation. I don't see it.
So, boss, I was wondering when you do an
It is
observation
strange. Yeah, go ahead. Go ahead.
in
Question.
Afterglow, when I go to the header, it seems like the date should be in there also, right?
Which one?
If you go in Afterglow, I was hoping the Julian date would be in there with the raw header data, and I do not see that. I thought that would be where to be.
Because right now we are not on the afterglow. We are on the Skynet at the moment.
Okay,
Because
that's
we
good.
want to take a picture first and then we go afterglow. But right now we're just trying to see, find the what they call it here. It gives, for example, let me. Oh, it might be we're gonna go on the next items. For now, we just choose the what to call it, Junes and Jupiters. On the filter, probably we're gonna go on the filter options. Let me go on the next phase. No, it is. Let me see. Let me go back from the beginning. This is Jupiter. Search. I found the Jupiter and we say Jupiter moons. You can identify any other object that you needed here. Then you're gonna go save and choose the filter. Filter on the Jupiter, as we mentioned, is gonna be V. And we come to V. And after that, we go to the telescopes and we choose all the telescopes. And we go save and continue. Okay, here, let me see if we go this one, 0.03 duration. Okay, here, probably in here we have to identify the, that's strange. Because in here it says under the advanced tab, uh, select the request, repeat 14 times per day. Continue the next one. Now continue the next. Okay. This is the kind of things I don't see it, advanced options. I use it before. I don't know, something happened. Okay. Oh, here. Advanced option is here. It's hidden. Okay. Therefore, this advanced option is not at the beginning, at the end. When we're choosing the filters and the duration, we're gonna go 1 here. And then we choose the sequential filters, continue
You
and serve,
you've
and
got
repeat.
those switched real quick, Abbas. You had the number and the exposure backwards, I think.
Do you see the screen right now or no?
Yeah, yeah. Go back up to your number of exposures. Just put one in there. You have 0.03.
I have to
Your
make it.
duration should be 0.03, right?
Yeah. Oh, yeah, yeah. You're right.
Yeah, I got those switched.
I made a mistake. Yeah, that is correct.
Sorry.
Yeah, duration gonna be 0.3. Thank you for correcting me. That's one exposure, 0.03. That's correct. And here we just specify the advanced option, sequential filters. Continue to next available. Repeat how many times? 14 times, and then 1 day uh, apart at least, and then save and continue. As you see it here, you again double check to make sure everything is correct. And based on that, you see that's gonna be around 14 credit gonna take from you. And when you are comfortable with that, you can hit the submit and proceed to observation to collect the pictures. Any
Yeah.
question on this practice?
So you have to realize this will take 14 days, 14
Minimum,
times
yeah,
one day between each. So it's going to take 2 weeks to do all these observations.
yeah,
That'll be one thing we'll have to get kicked in right away. You have nothing to work with for a couple of weeks. Actually, that's not true. You'll get images as you go, but all of them won't be done by 14, I would think.
yeah, yeah. It's gonna be 2 weeks. It's gonna take. Therefore, if probably you can. And you can do it for either of the gas giants, for example, Saturn or Uranus. And the other gas giants are a little bit easier because you don't have many different moons. Only you have, for example, on the Neptune, Triton only is the only moon that you can observe it and easier to catch it. But on the Jupiter, you have to distinguish which one is the Ganymede. That's only a problem that I see it. But other than that, either of them you can choose it and make it 14-day observation. Any question?
How you doing? Okay. I was actually dropping those in
Okay.
right now myself. Get those going. Yeah. A couple things I'll kind of back up through. Thanks, boss. Is awesome. Um, If you want, I'll share my screen a little bit and go back through a few
Sure, go
things.
ahead.
Just a few, it's nice having it once through, then have a second through to kind of bounce through it a couple different ways. And actually, I have to change my windows real quick here. I'll be looking at the funny things here. Okay, so let's see what we got here. Yeah, is that screen coming up okay? You see that all right?
I can see it. Yeah, thank you.
Yeah. So it's a nice little simulation. Just going back to the Kepler's law, just the idea of when Kepler was going through this, he didn't have calculus, didn't have any advanced math. And this is an ellipse, so it's two foci. And we see a lot of Kepler's laws as he'd have them just kind of tied up in the motion of this. We can see very clearly it's going slow as things are far away. As it comes up closer, it's going to speed up. And the definition of ellipse is something where you have basically you pick any point on the edge, and you draw a line between those 2 points, that sum always stays the same, and that sum is always the same as the major axis, the sum of that. And so a couple things you wouldn't know, I think, looking at this, but if you do take an ellipse and you drop those two in on top of each other, this does turn into a circle. So the nice thing, we've talked this in class, I think, before, but that is why you can get away using a lot of the same physics for a circle for an ellipse, is that it all basically washes out the same. So is r cubed equals the r. Let's see. Let's switch to another one real quick here. So faster, slower, we got that. I'll close that one out. But we watch how these things go around. It's the ratio of the period to the distance. If I switch this to a circle, the laws that Kepler gives us is basically the same thing. It's same. Um, and I can reset this again and get that going here. I think this actually allow me to add the strings to it. So it's kind of fun to see how that's what those D1, D2 are, that's it. I was hoping this thing would allow me to move something, but this is a PhET simulation and it's just not doing it. So I was kind of bummed that that would happen. And we can see how the gravitational force is working. Okay, so a couple of notes I had, we'll make sure I don't skip, that I kind of go through this, is that the original idea was that everything would move in perfect spheres. And so when Kepler gives us this shape, the ellipse, I think it goes much beyond that he's actually talking about all conics. He'd be very familiar with doing conical math. And so a circle is a beautiful circular shape. But if you start to break that circle into two foci, you end up with an ellipse. And if you break it farther, it goes into a parabola and it gets hyperbolic. So you get all the conical shapes of everything in the solar system comes out of this relationship with how things kind of go around each other. And one exception we are making where this actually doesn't simplify is we are assuming that the sun doesn't move at all, which is pretty close for us and the sun. But we do know that the sun does wiggle a little bit, so technically it does throw your relationship off just a little bit as it goes. All right. And going back to our discussion, I'm going to go ahead and end this. So a couple of things we're sharing. Because I knew recording this, I thought I'd throw this stuff out here. But number 14, welder's glass, works really nice for observing sunspots, just like Galileo did. It's just amazing. He started observing our sunspots back in the 1600s, and that never stopped. And so our progression of data goes all the way back to his time, which is just amazing. All right, I'm just checking my boxes. Okay, conics, central masses. All right, so boss, that's what I had. Just a few things trying to fill in the holes a little bit.
Very good. Thank you. That's a graphical representation of the ellipse. Excellent. I like it. It's way that it shows how they move planet around the major axis and they create the orbit. That's gonna be essential and good for us. The other thing is that I have it in here in my hand. Let me share it with you. And here, just quickly.
Yeah. If we have any trouble putting in observations, is it all working well for you for Skynet?
Yeah.
Okay, good.
Okay. The things that we are looking right now, we just observe it. One of the key features about the parallax on the lab one, but is actually this is kind of things that we have it on the this lab tree that we're gonna look through it. We're gonna look through it different way. Here is if we're gonna, for example, if we consider Earth moving around the sun, and this location on the February, we see it the Pleiades on this direction on the sky. But on the August, when we observe it, we're gonna go a different location because considering the Pleiades is very closer to us than the very background, far away star on the sky. Therefore, based on this different location, it might be very small. It's going to be zero point 0.1 degree or something like that. We can measure this parallax angle, and then we calculate the orbit size. This is one of the key things that for checking the orbit initially they created by that one. And also at the same time, if we compare in this one with the Kepler's third law, that this semi-major axis gonna be power 2 proportional with the uh, orbital period t, that is also create another way. This is two method of the measurement of the distance for the orbit that we had, and each of them they have if for this exercise that we're gonna have on the lab, we're gonna have some comparison between these two and how you feel the uh, size of the error that might happen for any of these two different distance measurement. As we mentioned on the uh, labs that we're gonna go on the curriculum based on the distance ladder. We started with the Earth. We measured the Earth circumstances and circumferences and also other longitude and latitude coordinates here. Then the next step we're gonna go and in here on lab 3, we're gonna measure the orbit dimensions, either mass of the major body that is on the orbit, if we assume the orbit of the Earth around the sun, or m gonna be mass of the sun, and if we're gonna measure the, for example, parameter for the orbit of the moon around the Earth, the mass of m gonna be or mass of the Earth. And similarly, if we're gonna look through the Jupiter, uh, Jupiter mass gonna be for the orbit of the moons around the Jupiter, that center. That is create a simplification. Although we have a Jupiter, Jupiter, it is within a solar system, and the gravitational force of the sun and other planets nearby, like a Saturn, also may impact. But all of those gonna provide some simplification and kind of error on the calculation. But anyway, by this kind of simplification, only be just considering the gas giant, either for Saturn or uh, for the Jupiter or Uranus and Neptune, only we consider those as a kind of orbiting mechanism, and that's going to create a good simplification and get some idea about the size of the moons that we have on the those gas giant. Therefore, the activity on the lab is going to be focused either of that for gas giant, and also last part going to be on the Venus that we're going to go over on the next week on that. Any question on that?
I'm going to back up too. One thing I did notice,
Sure.
actually, I meant to say it before, but with our observations doing the moons around the planets, Jupiter's a go and Uranus is a go. Neptune and Saturn, you'll find you won't be able to get any images of those at this point because they're right lined up with the sun. And so that wouldn't even be available for another 2 months or more, just FYI, for going back to that observation to get that moons. So all we're really expecting on this one is be able to get some data for Jupiter and get data for Uranus, and that's going to be good enough for what we're doing.
I think that's going to cancel out two other options.
Yeah,
By the time
but
that we have. Therefore, either we can use Uranus or Jupiter. That's gonna be also good. And also for the, let me show you another one activity. Let me, as we have time here, uh, another option.
Yeah.
Let's,
I know there's a little out of the blue there, but nice discussion too, boss, with what you're sharing with Pleiades.
pardon me? Yeah,
I was
okay.
kind of going back, way back into the lesson as you were moving
Yeah,
forward. I just
yeah,
forgot to
yeah,
say
yeah.
that earlier.
Yeah, yeah.
So,
Thank you. And let me go back on the here. Okay, let me go to the sky, since it's Skynet, and we see observation. Then we go some
I'm
of
gonna add
the,
one more thing as you're setting up here real quick. So things
sure.
I forgot to say. I always look at my checklist, make sure I'm covering all the little details. When things are orbiting, and this is just for the recording as much as anything, the central mass is the mass that drives everything. The mass that's going around is very insignificant to getting all this, unless the moon is as big as the planet, which does happen. So Pluto does give you a weird data compared to the others, but all the others, the moons are much smaller.
Yeah. Thank you. And also, that's a good point. Thank you, John, on that. If we go to the, for example, this is one of the pictures that I took at with Jupiter long before, and you don't see it. When you start this Skynet, you don't see it. You have to go to the Sky Glow and Afterglow, and then sign it on that. And here you will have to, if you don't have it, you bring it to your workplace. Then you search for Jupiter. No, you don't have it. Go back. We just upload it here, probably. Upload. No. Mm,
So, Avery, any challenges you think with looking at Jupiter and its moons? You anticipate trying to nail down Ganymede? We're working on it.
I don't know how like good the resolution is if like a moon is in front of Jupiter. I don't know how well the brightness will pick that up or if that'll be very visible. But
That's a good point. It could be possible you don't see it. It's not going to be there. And plus, so usually when we look at Jupiter, how many moons do we normally see?
like five-ish max.
So picking up Ganymede might be a bit of a challenge. It's big, but I think I have to use stellarium to really verify which moon is which.
yeah, I get the Jupiter's orbit. As remember, Jupiter orbits, we just say it V14, and we just upload it again. Reduce images. Then, and here we can show it one of the targets and make it a zoom to fit. And bright object, you see only Jupiter. Then you bring it saturation level down, or you go at with this one and bring it saturation up to see it more closely. And then the next step gonna be here is good enough. I think something like this over here. Then you can see it and you can bring it on the middle as you see it more closely. Probably one of these gonna be Ganymede. How we can identify which one is the Ganymede? We have to go to the here data, the time, and whatever we taking picture and date, and we check from the stellarium to see based on this orientation which one is the Ganymede. And then based on that, we're gonna come on here and identify uh, which one we needed, like a centroid click, and also like here, for example, we identify this and we make a measure from the center of the planet. And that's gonna give us the distance on the here, length, how much we have. and that's gonna provide some information for us how much the distance we have it here, but this is one of them. We're gonna have 14 different uh, measurement and pictures. This is one of them, and we have to do it repeated for all of them. We see which one is the largest one, and that's kind of create for us that how we can create a graph to see which one is the semi-major axis of the this Ganymede from the Jupiter gonna be. And that's also there is a tutorial on the lab tree. You can look through it. That is then recorded previously to detail analysis of that. And also we can go over on the next session for next week to more detail both on this and also uh, um, Venus measurements for the phases. Any question on that? You see, this might be very simple, but we have to repeat it myself. When I don't repeat it in next week or 2 week, I may forget myself. That's easy. When we do it more often, we can remember it, the things that we needed to do.
This is why I feel like an astronomer. We're actually doing the measurements and checking things out from the slides.
Yeah,
Um,
exactly.
See how I can use this in astronomy class in the future. I know we can share files. I can save these images that we have a good set of images.
That's right.
Probably do with the different moons of Jupiter, have people try different ones in afterglow and see if they couldn't get better value with some moons than others.
Very good.
Yeah. I'm not sure which moon is the farthest out. If Ganny is the farthest, I should.
Might be. I don't know. We have to check it. That's the reason that one of this activity has to be done in parallel with the stellarium to make sure that we identify which one is the Ganymede for that 14 observation for each of them separately. And that's going to be easy way of the frequency, figure it out which one is the Ganymede and get the data and put it on the data sheet. And also another thing I forgot to mention, let me quickly go here. Another item that we had, and here, let me see. This is
So I'm seeing that Ganymede's one of the farthest. Of the major four, Callisto is the farthest out, and Ganymede is next. So those aren't the best two moons, I'm sure, to do this with. And Ganymede's just so big, you can't miss it. But Io just pops around so fast, and Europa is real close to Io. So, all
yeah,
right.
and also I'm gonna provide this information here, as you mentioned, for the graph of the to getting the uh, angular separation or kind of other activity that, for example, here for the major axis, we're going to use a tool that is created on Skynet. They call it Astromancer. Astromancer, let me see if it is, I had it in here somewhere. I put it, this Astromancer going to provide graphing, enough graphing tool that we have it. Let me see it through. I sent it on the email this morning. When you go Astromancer, it's very lab program. You don't need it to download anything. You have here several options. Mostly we're gonna focus on the curve. Then we put some data on the curve here and we get the data. If we change this values, sorry, for example, we put some random number, it's automatically going to change the graphs that we have. We can have multiple graphs. If we want to have 4 graphs, we can have 4 data, all of them. Something we can provide data here. That and each of them with different colors. And
Yeah, finding the Astromancer, actually just do a web search and it pops right up. Now, I did use it before, so I'm sure it's a quick pop up on mine, but it is just astromancer.skynet.unc. I mean, it just comes up as a free app.
yeah, and also you can assign the label charts, for example, provide a title for it, and what's the x-axis, what's the data that you have it. You can reset it those and identify it to make it more elaborated here based on the tutorial that we have on the WebAssign. And then based on that, we can save the graph and we give it a name, for example, whatever you put it here, and it's gonna show it to you as a JPG file. This is the file that you're gonna upload it on the uh, program that we have on here on the this area that after we get the graphs. And the thing is that we have to move it around. We may have different points like this data point that we have by the red circle is showing here. But when we have on the Astromancer, we may have different data in here. We have to play with this um, kind of numbers that we have orientation to move it around and set it on the way that is matched with the correct orientation of the value on here. That we're gonna discuss on the next week of this session on the March 16 next week.
Any questions on any of this?
Yeah, no, thank you.
Thank you, and hopefully, I think we have around 2:54, about 6 minutes. We can save a date if you don't have any question. But just let me know if you already have access to the WebAssign. Is that correct, Avery?
I don't. I've just been using the materials that like you've been sending out on email.
But is there any issue that you can do that? We can provide support for you for the payment if you think is needed.
Thank you.
Yeah, if you wanna, you can send it the information. I will, as I send it on the email, we can do that to because when you do activity on the WebAssign, it's totally different than the Skynet. It's gonna be you're learning more items with using the Astromancer, using the WebAssign tool to saving the data. That's gonna be more interactive way than only taking the picture. Just let us know, either John and myself, and send it information that you needed. We can support the. I will send it another time email to ask everybody that please do not hesitate. This is the we have some um amount of the money put in aside to make sure that everybody has access to this program and that is supported by the National Science Foundation. And therefore, this is the way. Probably next year we don't want we cannot do that, probably. But this is the year that we have it. Opportunity is better to use it. Thank you.
Thanks.
You're welcome. Anything outstanding item you're gonna ask or add at the end, John?
I think we're in pretty good shape if nobody has any other questions. And that was pretty smooth going through. I think we're getting kind of a niche with what's happening and used to using the programs. I would say, yeah, don't hesitate to reach out about the WebAssign, get that set up, and we'll make sure we are in good shape going forward.
Thank you. Have a blessing day and a good
You
one,
too.
and enjoy the day and relax for the next week.
Thanks. Thanks, boss.
Okay.
See you.
Thank you. See
Thanks.
you.
See you next
Bye-bye.
week.
Bye.